the Data Science and AI User Group. Today, my name is Brad Miller. We're going to be introducing Michael, and Michael McGuire is going to be giving us an amazing talk today on computer vision and artificial intelligence. So, just as a brief bio for Michael, he attended UIUC, graduated in 2020 with a computer science degree. During his time here, he studied AI, computer vision, robotics, principles of software design, and then as a student, he led the special interest group for AI and data analytics, and a student organization under the ACM. So Michael's worked at EarthSense, an agricultural robotics startup company, since he was an intern there in 2020. In his 5 years at EarthSense, I believe it's 2025 already? Oh my goodness. He's been involved in a whole bunch of projects using AI and robotics, including some sensor-based high-throughput plant phenotyping, as well as vision autonomy. In his first 3 years, he primarily focused on developing precise vision-based algorithms for counting soybeans, estimating the height of corn ears, and measuring the width of corn stems. And then since 2023, he's led the EarthSense vision team, developing perception algorithms that enable the robots to drive themselves autonomously through cornfields, oil palm orchards, grape vineyards, solar fields, and much more. So he's really excited to share with us a little bit about his experience, as well as all of this cool stuff with AI and computer vision. So without further ado, let's welcome Michael.
Thank you for that introduction. Thank you everybody for coming here today. It's an honor to be here. We used to work in this building, EarthSense. We have a couple of offices here, one of them right there, so it's kind of nostalgic to come back and talk about what we're doing and give an update. After all these years. All right, so I'll just get into it. So, my background, you went into it a little bit, but just a refresher. What I'm showing here, main point of this slide is that I've kind of always been a geek, AI and games and all that stuff. So I did a bachelor's at UICS, graduated in 2020, involved in the AI club. I interned at a couple companies, one of them out of town, but one of them at Synchrony just across the road over there, Synchrony Emerging Technology Center, right here in Research Park. I joined EarthSense in January 2020, started out as an intern, and have stuck around for 5 years, working on vision primarily. And basically I've just been tinkering with AI for years. What we're looking at here, that visual is the first AI I ever generated to play Breakout, it's called. So this was a fun little project from the days before ChatGPT came and made stuff like this look, old-fashioned. But this was a fun way to get into it. And so, just one more thing to show. So this is a game, StarCraft, a complex strategy game, and I thought I would show it just because this is actually how I got into AI in the first place. It wasn't really about work or career or anything like that. I actually wanted to make AIs that could play this game, which, as you can see, it's quite complex, lots of decision making, lots of fine-grained control going on. But anyway, this sort of thing got me into AI, got me into robotics, and all sorts of these automated, complex decision-making things that we're doing at EarthSense today. All right, so now I'm going to talk a bit about EarthSense. Those who have been in the Research Park community for years may have heard of us, seen our robots years ago. For those who haven't, we're an agricultural robotics company. We make robots that are trying to heal the planet, address problems that farmers have, and that various problems the world has, basically, that can be solved with outdoor robotics primarily. And towards that end, we have a suite of robots that we've delivered, and I'll go through each of these in turn in more detail, but you can see them from left to right there, roughly in order from smallest to largest, as well as oldest to newest. But we have our TerraSentia, our TerraSentia Plus, our Terra Preta, and our Terra Max robot. So I'm going to go ahead and go through these. So we'll start with TerraSentia. So this was developed for plant phenotyping. Basic idea here was monitoring the traits of corn and soybean and other plants. So a very small rover, drives through corn, has cameras and LiDARs on it. very lightweight. Here you can see it autonomously navigating through a couple of outdoor crops. Here it's going through puddles, like no problem. There it is going through corn. Yeah, all these things. So that's TerraSentia. Here we'll talk about TerraPrep. So this is our platform for autonomous cover cropping. If y'all have farmer friends, go ahead and ask them about the benefits of cover cropping. They're good for the soil and the environment in all sorts of ways. And what we're trying to do is deliver a solution that can plant cover crops at scale at the best time of year. You can see here a visual of what it looks like to be planted with a traditional method with tractors versus what our method looks like. So there's our robot going through the corn, driving itself, and spraying seed as it goes. So yeah, here we are running through corn. All right, so we're going to step away from corn for a bit to look more at orchard robotics, plantations, orchards, vineyards, and that's for TerraMax. And so TerraMax is our solution for all of these things. This is a much larger robot, roughly the size of a minivan, much heavier, all those things. And so we're basically taking our know-how from working with small robots and adapting it to larger robots and transferring our knowledge over. Here you can see it going through a beast of a puddle. And our team did a great job making a robot that could just go through those like it was nothing. And here you can see it spraying as it goes. So the idea is that this is going to provide treatment in orchards, vineyards, plantations, all these things. Lastly, let's see, I'll go through the TerraSensia Plus. I always love sharing this video. So this is our general purpose autonomous robot. It's about the same size as the TerraSensia. One of our star actors in this video is at this table if you want his autograph. And yeah, so TerraSensia Plus, the idea is to generalize the capacity we developed with TerraSensia and basically make a robot that can go anywhere outdoors, navigate through various difficult terrains, tell where it's going, and deploy real-world intelligence wherever the customer may want it to be. Yeah, so I'll talk a bit about how we got here. And I'm going to do this mostly from the view of vision, because that's what I've been working on for the last 5 years. There's plenty of stuff that has been going on that we've made great progress in the last several years in hardware, software, all these things. But I'm mostly just going to talk about what I've been working on, since it's what I know best. But yeah, I'll give the background. So first I'm going to talk about phenotyping. So I mentioned this a bit earlier, but this was where we got started. The basic idea here is that farmers and breeders, they want to know as much information they can about their crops as possible. And one solution that we came up with for this was to deliver a robot that can provide these phenotypes upon experimental units of corn. Basically, you can imagine like having a 5 or 10 meter long stretch of corn or soy or whatever it is, and you want to go ahead and measure every plant in that, get an average of certain traits, such as stem width, plant height, corn ear height, things like that. And the idea was that we would go ahead and do this analysis. We would tell the breeders which plants have the best traits, and they would go ahead and make decisions and build smart crops from that. And so here's sort of the pipeline of how we did it. We had, from the beginning, the conception was we have the robot in the field, the human drives it around, it gathers data in the field, and one of the first things we do is we upload that data, we analyze it, we process it, and we train up some neural networks and some algorithms, and at the other end, we have information about the crops and then better crops by design, as it says up there. So, robot in field, data analysis, information about crops, better crops. So, to go into how we do this, the first thing we have to consider is data. So I'll just briefly go through kind of what we have to work with here. So basically at a very straightforward analysis, it's camera data, LiDAR data, and GPS data. I'll show a video here of what our camera data looks like from our TerraSensia robot. Has multiple cameras on it. Here's a different configuration for our TerraSensia robot. These are both from different stages of corn, that sort of thing. I guess that other video isn't playing, but the other video was going to show the LiDAR. But anyway, I'll get into the first project that I ever worked at EarthSense. and that is soybean pod count. So I guess as a fun little question to the audience, like if you're going to try and do something like count how many soybean pods there are in a stretch of soybean plants, how would you even start? Anyone want to guess any random ideas?
Count one and estimate.
Count one and estimate? One soybean?
Well, count one plant.
One plant? That's a good idea, yeah. If you can get one plant, you can go ahead and count how many plants there are, multiply that by how many are on that plant, and you'll have a good estimate. But from there, all sorts of other questions come up, like how do you get the number of soybeans on one plant? How do you even know what a soybean is or where it is? How do you make sure that you have the right data to do it? Do you use neural networks? If you use a neural network, how do you train it? How do you get a data set? How do you label it? All that sort of thing. And so a whole systems problem emerges once you even start considering something like this. So this is a fun project for me to start about because this was actually the first project I did when I joined EarthSense. I was basically hired and then immediately told, all right, figure out how to count the number of soybeans in a certain stretch of plants. And so this is the first visual that I ever sent in the EarthSense Slack of how our soybean pod count algorithm was doing. And so we're getting some of the soybeans, but there's some weird things going on. We're not seeing the whole plant. And so this was my first introduction to the whole rabbit's hole, the rabbit hole of vision development in general. So yeah, at that time we didn't have a lot of infrastructure that we do now. We didn't have a labeled data set. We didn't have a very good neural network for soybean pods. We didn't have tooling for working with our data and all that stuff. And so it was interesting to build a lot of that stuff up from the ground up, basically. But over the years, over the next year or so, we underwent a couple of stages of iterative improvement. We went ahead and we added a better camera on the robot that could see more of the plant. We developed a labeling service that we could use to go ahead and do our own labeling. And from there we went ahead and trained up a soybean detector. And what we got, let's see if this video plays. What you can see here is an improved soybean detector running on all the images. And as you can see, it's getting a lot of the small ones all over the place. Very messy data, but in the end, we'll see the next slide. Oh, forgot to share the correlation graph, I suppose. The end result of it was to show that we were able to correlate and predict with the true number of soybean pods that were measured. Something else I'll show, plant height. All right. So here we can see some of our LiDAR data. So we went ahead and we generated LiDAR point clouds for every plot that we're working with. And so from here, we were able to go ahead and find where the highest parts of those plants were and extract out an estimate of the height of the plants. So you can see from looking at that video, there's a pretty clear view of the structure. And so once you can get a point cloud like this, it's pretty straightforward to go ahead and estimate it. Yeah, plant height's a little bit of the odd one out because it's LiDAR data rather than image data. Now I'm going to talk about a fun one called leaf area index that we did. So here we were working with trying to basically measure how much light was coming through the canopy between the corn leaves. So what we're seeing on the right is basically a metric of what's sky versus what's not. And so once you can find what part is sky and what part isn't, you go ahead and you get a pretty good estimate of what the leaf area is. So we can see on the right, the red pixels correspond to sky. All right, so now we get to a really fun one, stem diameter. So this was interesting because it was a step beyond soybean detection. Not only did we have to detect these corn stems, we had to actually get a very precise estimate of their dimensions, and specifically their width along the horizontal axis. So as you can see here, we trained up a neural network that could go ahead and detect these corn stems. So we had to rework our system to work in, basically working with masks here, very precise pixel by pixel maps of where each stem ends and where it begins. And we had to combine this together with other data from the robot, such as its GPS, its speed, its estimate of where it had moved, and that sort of thing. And then we moved on to another even more challenging problem, corn ear height. So this was one where we had to detect corn ears, we had to track corn ears, and we had to estimate how high up they were off the ground. And one client in particular was very picky that we get it within 5 centimeters on average. So that's 2 knuckles on your index finger. So from this data, we had to go ahead and estimate their height within that amount of precision. And so this one was interesting because we had to introduce a new sensor for this, a depth camera that was able to get the 3D location of the corn ears. But it was able to build off of everything that we did in the previous experiments. We just had to adjust for the new sensor and the new geometry and all of these things. So how do we evaluate? So what we're going to show here is the results that we have for these different traits. So for all the traits I went through, so the pod count, that one's shown on the right there. We have a correlation of about R equals 0.67 on a data set of yield measurements that they took. And then on the left, we have different graphs for the other 4 traits: stem width, ear height, leaf area index, and plant height, all with very strong correlations. And so ultimately, the end result is producing a number per plot, indicating what that trait value is, and then validating that it reproduces what a human would get if they go out there and measure it themselves. So from the very early stages, we've been focusing on making vision algorithms that can get precision as high as possible, down to the centimeter if possible, because every centimeter makes a difference. Yeah, and so here I'll just go over the workflow again. With the data as seen before that we gathered, the robot gathers in the field, we go ahead and we validate the data. We run our algorithms on it, our neural networks, and everything else, and out comes the result per plot. All right, so that was the first 3 years of a lot of what I did at EarthSense. There were other people as well. It was a very large team effort. Had lots of help from our hardware and software teams as well, helping us to have a very good robot, very reliable robot, all these things. Yeah, and so I'll talk now about vision autonomy, which is something that we shifted towards going forward. So this was interesting because in the first 3 years with phenotyping, we were largely assuming that we could run offline, like we could run on cloud GPUs. We don't need to have small neural networks. We don't need to run fast. We have as much time as we need, basically. But when we started shifting towards vision autonomy, now we have to make decisions very quickly, very frequently, many times a second, and it just requires a total rethink of how we do things, basically. But what I'm going to go through now are a couple of applications where we deployed vision autonomy and had promising results. So I'm going to start with Terra Preta. So this is our cover crop planting robot that I talked about earlier. Here you can see a sped up video of it going through some corn, navigating entirely autonomously, running purely off of camera data. So you can see some of the challenges here. The corn row is very narrow. Every centimeter counts here. And so that's always something that we're trying to do, shave off every centimeter of area that we can. So this consists of a couple of steps, one of which is autonomously going down the row, which is hard enough. But every once in a while, the row runs out, and then we have to turn around and go and enter the next one. So it's multiple complex problems wrapped up in one in sequence. And as always, our goal is to make it as reliable and flawless as possible and fast, all these things. So I'm going to show some visuals now of what Terra Preta, oh, hold on. Oh, it's not liking me. Let's see if it'll, thanks. Yeah, so this is the first brief clip of what Terra Preta sees as it's going through row follow. So this is all just running with a regular old camera. It doesn't take anything too fancy, but we go ahead and we just have it pointing forward, and we trained up a very lightweight neural network that will find these vanishing lines. These disappeared now, but from those vanishing lines, we're able to get a good estimate of where the robot is in the row, how close it is to the sides, how much tilt there is relative to the corn rows. From there, we can tell on a low-level controller how much the robot needs to turn to straighten itself out. Here, we're looking at a depth network. Yeah. The last part there, we were looking at a depth network that can also show us how far away each pixel is. We can do all sorts of processing to get very high precision estimates of the side distance, especially in complicated situations where there's occlusion, sometimes there's a gap in the corn. So yeah, we have multiple different methods that we use to get row follow to work here. So what I'm going to show now is what we're working on for lane turning. So as I mentioned earlier, one of the complicated parts of this problem is making sure that our robot can turn. And so we want to be able to make this as programmatic as possible because we want it to generalize beyond just cover cropping and to generalize to robots that will be deployed in corn in general. So something we want is the ability to have an exit a row and then cut across maybe 1 row, 10 rows, 100 rows, but keep very accurate track of where it is and then turn back in. And so what we're looking at here is we're working with a stereo camera, some color and depth data, and it goes ahead and tracks where it is very precisely. So here we're working with a SLAM algorithm. For those who've worked in robotics, they'll be familiar with that. The goal here is as much as possible to track every centimeter of displacement that the robot has, shave off every centimeter of error, and make sure that we can exit the row, navigate, and re-enter as accurately as possible. Yeah, so all of this has primarily been oriented towards these problems, row follow, lane turning, and the fact that there's very little room for error. To put a number on it, corn rows are typically 76 centimeters wide. I think the robot, last I checked, was 45 centimeters wide. So you can do the math, it's about 15 centimeters on each side, and any shift one way or the other can very easily throw it into a row of corn and run over a bunch of plants, which we don't want. So yeah, those are the challenges from Terra Preta. So now I'm going to talk a bit about TerraMax vision autonomy. So here, just a reminder, this is our TerraMax robot again. So here we have a totally different set of environmental constraints. One way that this is easier is that we have more space. One way that it's harder is that now we're dealing with a much larger robot, there are safety concerns, we have to be a lot more careful and much more fault tolerant, these sorts of things. And so what I'll go to the next slide. Yeah, so I'll go into what it sees. So the good news is that we can actually reuse a lot of what we used from Terra Preta. So the basic core concept here of the vanishing line approach, which we saw in the previous slides with Terra Preta, this still works here, so we can get a pretty good estimate of how far we are from the center. And so that's the first part of what TerraMax sees. But it's not enough to just see where you are in the row. You also have to detect things that are coming up. You have to detect trees, you have to detect puddles, obstacles, humans, anything that comes up. And so what we have here is a method of detecting these things. In a bit, it's also going to show the depth channel. It's very important that we can see how far away things are. So there you can see a color coding of how far away things are. And when we put all of this together, what we eventually get is a grid map. So here we can see a freeze frame, there's a raw image, some detections, and our depth. And what we're trying to get is a top-down view of where everything is. So as humans, we can see everything, right? We have a very intuitive understanding of where things are. But to a robot, we have to make it as simple and as dumb as possible. And so what we have on the right there is a couple of things that we're visualizing, one of which is the pathway on the ground that it can travel straight through. And the others are, you can see 5 trees and a triangle pattern that it has there that we're going to make sure that our algorithms know to avoid. So with this information, the robot knows, go ahead and drive straight, don't turn left, don't turn right too much, and that sort of thing. And so this is part of our solution for handling more than just the row follow problem. It's also for how we're going to handle lane turn. It's how we're going to handle all sorts of issues. Here we have another video of our neural network detecting things. We have to tread a very precise path here as we do a lane turn. Yeah, so the challenges here, there's a few more of them than there are with Terra Preta, primarily because of safety, the high cost of running into obstacles. If the robot crashes into a tree and just breaks, that's like a $50,000, paperweight that we so we don't want to have that. We want to make sure that we're not hitting into things. Yeah, so these are some of the challenges with these robots, and as always, trying to make everything run as fast as possible. It's a very different paradigm from working on cloud, working with LLMs, working with these things. We have to make our networks as lightweight as possible, make them run as fast as possible, use up as little compute as possible. Yeah, so I thought I would talk a bit about our long-term plans. The basic idea for vision and autonomy long-term is that we want to move beyond just working with these heuristics, right? So currently we're training neural networks to detect very specific things and applying algorithms to them to localize where things are in the environment. We're hoping to leverage the work that's being done lately in large language models, vision language models, all these things, these new approaches that are coming out to produce robots that can be more proactive in their thinking, and they can handle more complicated situations perhaps without having to be hard-coded to do anything. So these are things that we're thinking about, but just in general, providing generalized outdoor autonomy is another one. We don't want to just get stuck to porn or to agriculture or to anything like that. In theory, we think that we can handle the generalized outdoor problem, detecting things, navigating around them, depending on what the customer wants. And so we're always looking for ways that we can improve our systems to do this. This sort of ChatGPT for navigation, and just to have a system that we don't have to fine tune and manually put in all these hours of effort into, but to have something that can be truly autonomous, truly thinking for itself in general. So yeah, these are some goals that we're reaching out for. So yeah, I'll just go in a bit into the technologies that we use. So at a high level, we rely on neural networks. It's a very big part of what we do. We train on neural networks for the vanishing lines, to detect objects, just to tell us where the robot is in general. We're also working, however, with older-fashioned computer vision technology, older algorithms, things like that. We're also working with SLAM, which simultaneous localization and mapping, which our roboticist friends can tell you more about. And yeah, we're also heavily using depth and stereo cameras, LiDARs, GPUs on our robots, GPS, and that sort of thing. And so it's a whole bunch of things that come together. And this, of course, there's also the work that our hardware team does to make sure that we have high quality, reliable robots, and that sort of thing. So it is a team effort. It takes a lot of things coming together. One thing that people can over-focus on is neural networks. Neural networks are great, but they do need a lot of support and a lot of help and very good data put in order to work at their best. So I thought I would just talk a bit about the areas of development in vision. So here I'm sort of looking back at 5 years of work and kind of the things that I've learned. So to echo what I said on the previous slide, it's easy to overemphasize neural networks. They're very important for sure. But something I'll just go into is that you also have to consider the whole system. So you have to consider your sensors and your compute. Do you have the right camera for this task? Does it have the right field of view, the right resolution? Are you seeing too little, too much? Is the brightness right? You need to have enough compute to handle however many, like everyone wants to put like maybe 20 cameras on a robot, but a lot of computers can't handle that many. And if you want to run algorithms, you need to have the right compute on your robot to handle it. Ideally GPUs, but sometimes you're cost constrained, that sort of thing. And so there's a whole systems problem that emerges just when you're at this point with sensors and compute. Another big one is data management. So even one way to make neural network development and training and processing a lot easier is to have good data management tools. So we at EarthSense, we have terabytes and terabytes of data that we've gathered from our many robots out in the field. And it helps to be able to query and access that data automatically, have it stored in a reliable, structured way, and then we can go ahead and very easily do large-scale operations with it. We can also talk about labeling and data sets. So we do all of our own labeling in-house. I remember in undergrad, in my courses, they taught me how to train neural networks once you had a data set. To echo my experience from the soybean podcast story earlier, we didn't have a data set when we started, and so we had to go ahead all the way. We had to go through the dependency chain all the way back to square one and get a labeling tool and label some data and build a data set, and then we could train a model. So here, neural networks finally make their appearance, first among equals. We can talk about algorithms. These are their own area of development. A good neural network is helped out by a good algorithm. They definitely both need attention. And then last I'm going to say is visualization. And I very strongly believe that visualization is key to understanding how your algorithms work, how they don't work. As you can tell from this presentation, I put videos, images all over the place. I like to visualize things. It's my primary way of understanding the problem and understanding the solutions and that sort of thing. So one thing that I've learned over the years is that we need to avoid just looking at neural networks, and we also need to make sure that the other pieces are in place and getting enough attention. And once those are in place, you can train very precise neural networks, train very high quality algorithms, all that sort of thing. Yeah, so now I'll just go through my advice, the lessons that I've learned deploying real world AI that I think that our team has benefited from, that I think other teams could benefit from as well. The first one will be to start simple. So a fun story about that soybean pod count problem is that from the start we thought, okay, we need to detect them and we need to track them. So between frames 1, 2, 3, 4, 5, we need to see that this is soybean A, and we can make sure we have the same soybean in each frame. And so we spent months and months working on that. And then one day one of my colleagues just chimed in and said, why don't we just take a picture every 5 centimeters or so and just add them up and see what happens? And we did that, and then we got good results. And so that was an interesting lesson in how we instantly went to thinking we need a complex solution for this, but we actually didn't. And a neural network that was detecting, every soybean in an image, and then you just add up image 1, image 2, image 3, image 4, that actually did pretty well. And so that's an interesting story to look back on for that reason. And so in general, we try to start simple whenever we're working on new vision and AI projects. Yeah, it's very important to consider the whole system. We've often found that a problem is made much easier when we added in a different camera, different field of view, that sort of thing. And sometimes we have assumptions about how a robot needs to be a certain price, needs to be below a certain cost threshold. But even if you look at the business model of it, you can discover opportunities to sort of increase the budget that you have for sensors on the robot, things like that. But just in general, between sensors, compute, algorithms, there's a whole bunch of things going on, and you might have something that works offline. You might have a Python script that can generate a solution that looks very good, but maybe it doesn't run fast enough on the robot, or you don't have the right cameras. So you got to look at all of these things. It's not just neural networks. This, I think I talked about on the previous slide, so I won't repeat myself too much. Yeah, I would say focus on the support. Yes, this also ties into the point in the previous slide. There are other things to kind of support the neural networks, such as good visualization tools, good evaluation tools, all of these things. It is some necessary work. And one thing that that I think has made my job easier is solving the general problem first. And one reason why that's helped is because we went ahead and we did that for Terra Preta, our corn robot, and we made our vanishing line solution that could tell where it was in the row. And then when it came time to make that work for TerraMax as well in the oil palm setting, because we had designed it in such a way that it could be reused, we just went ahead and copied a lot of functionality over there, and it wasn't very complex to go ahead and do that. And so this reflects our broader strategy of trying to develop generalized robotics, generalized autonomy. We solve the general problem and we prove a concept it and make sure that it works in one setting, and then we can deploy it more generally. Yeah, visualize everything. Make graphs, make images, visualize your neural network outputs, your algorithm outputs, your tracking algorithms, all that sort of thing. I find it extremely helpful. Sometimes the problem just becomes instantly obvious as soon as you visualize what's going on. All right. Should be another slide, I think. All right, so I'll close with this. Yeah, so broadly, yeah, these are my thoughts on how AI has shaped EarthSense, the work that we've done over the years, what we've learned, that sort of thing. And I'm definitely looking forward to us continuing to work on these things and make these great systems, deploy them in new environments, and yeah, just keep things going. So we're hiring for a couple of roles here. We're interested in exploring the field of generative AI in general, seeing how we can leverage the new work that's been coming out with vision language models, LLMs, all that stuff, and seeing how we can apply that in the robotic context, see how we can unlock a deeper understanding beyond just these high-level heuristics. And we're also looking for someone who can work on LoRa firmware. So these are very different roles, of course, but LoRa, of course, is very important as well for our deployment for Terra Preta, and basically making sure we can monitor our robots long range and make sure that if a robot crashes or needs help, we can go ahead and rescue it and that sort of thing. So, yeah.
So this is not LoRa adaptations in AI models, but rather
That's right.
This is LoRa as in like wideband, farther distant, like kind of.
That's right. Long range communication. Yeah, it's an unfortunate hash collision, but
Yes.
yeah. So yeah, that's definitely not LoRa for neural networks. I haven't worked with that too much. Yeah. So yeah, that's the presentation that we have. Let me know if there are any questions about EarthSense, about vision, about the roles that we have. Anything. Thank you.
I recently heard a saying that I thought was pretty interesting, but it said, look to what the nerds like to do at nights and on weekends. So what do you like to do at nights and on weekends?
Well, I like to exercise, I like to go on runs, I like to go on walks. I don't know, I'm kind of a boring guy, I think.
You don't do this stuff for fun?
Well, I get plenty of it at work, so as my boss always says, whenever you have free time, you must ask yourself, why do I have free time?
It's really great to see this being used in real-world applications. It's definitely a hard problem. I've done a lot of work with data labeling, so I'm very sympathetic to that problem. When you talk about wanting it to get to the state of using reasoning, could you help us understand, like, what does it not do now that the type of reasoning you're looking for would help it do in the future?
Yeah, it just comes down to the complicated situations. So for our TerraMax robot, for example, right now there's a lot of hard-coded logic around how we do turns. So basically we're assuming a map of like where trees are going to be. Basically, there's trees here, there's a narrow gap that we can travel through here, and there's a water channel up here. That if we follow the water channel, that's like the robot's cooked, it's finished. So we have a very narrow pathway to go through. But sometimes there'll just be like a tree between, say, the trees here and like so it'll be trees here, pathway, another tree, and then water channel. And sometimes the robot gets confused and thinks, oh, that's the last tree that I need to drive around. And so that's one case where a hard-coded heuristic just doesn't work. In practice, whenever we try to come up with heuristics to kind of think through these things, it ends up becoming tricky enough to where it's just hard to generalize. So that's one example.
Can I pause you there, because I actually didn't understand at one point when you were showing the design with the trees and the pathway, I didn't understand if you were giving it that ahead of time as a map of the place where it was going to be, or if it was extracting that from the visual things it was seeing.
I see, yeah, that's a good question. Yeah, it was finding that in real time. So the pipeline was images input, detections, it projects it using depth, and then it has an estimate of where everything is.
Okay.
Yeah. And we've explored working with maps ahead of time to get a sense of where trees are as something to help, just to help get a sense of how to make decisions, kind of localize us using geotag information.
But it needs to see both of those views because of the way the logic's implemented right now? Like it needs to understand the overhead view as well as the...
It needs to understand both, yeah.
Interesting.
So are these being used right now in like farms and stuff? And also, so some of the challenges that you talked about, like so finding the height of the corn off of the ground. So were those problems posed to you from your clients, or was that a part of like the?
It was from the clients, yeah. So depending on the robot line, we've had different levels of deployment. With our TerraSensor robot, we've been working with customers in the plant phenotyping space for many years, and so those have seen production use. Primarily, the customers came to us and they wanted specific traits for their plants, and so that's largely led these discussions, yeah. For our other robots, we're still more in the developmental phase, still figuring things out, but we're moving towards productionizing and getting use in real-world fields.
In terms of cost optimization, what are the areas which are the most challenging? Storage or cameras to make it more real world?
I may not be the best person to answer this question. Cameras, well, LiDARs are definitely something that you want to avoid if possible. LiDARs can just easily increase the cost of your project by $10,000. So we've deliberately tried to avoid some of the more fancy options there. So in that sense, sensors can be relatively cost prohibitive. Typically, I can definitely answer for sensors and compute. So robot computers can vary anywhere from a Raspberry Pi, about 20 bucks, to a Jetson Nano, which can be about 150 bucks, to some more expensive offerings, which will have GPUs in them, but might cost $1,000, $1,500. And so for some projects, we've had to go ahead and say we can't have a GPU on it, that sort of thing. And so that's always been a consideration, but in general, it's a broader consideration of what hardware parts do we need, what sensors, what compute. But it's also a question of like, how fast can we make the robot go? So like if we can, for the Terra Preta problem, for example, we figured out that if we can make the robot do lane turns very quickly, it actually enables us to do a significantly larger number of cover crop acres, which transfers into something like a 50 to 100% revenue increase. And so once you figure out you can do something like that, it unlocks a whole different budget sheet for how much your robot can cost and that sort of thing. So that's the best I can answer that, I think.
How tolerant are these robots to adverse weather conditions, rain, fog, sleet, snow?
We try to keep them out of the rain. So TerraSensor, covercrop, TerraMax, we try to make them water resistant enough to where if it starts sprinkling, it can be fine. Although, yeah, in general, we're not trying to weatherproof the crap out of them. I think with our solar robot, I might not be the best person to answer this. I think we are trying to make that as weatherproof as possible and waterproof and that sort of thing, yeah.
So what kind of algorithm, do they have to phone home to get the weather forecast before they go out? How do you keep them out of the rain?
Well, so far we've mostly relied on human-informed, like basically making sure the operators are aware of that sort of thing. In the future, we're trying to integrate our systems into a broader long-range management solution. So the idea is that eventually we won't have to have people take robots out to the field nearly as much. We'll have sort of like a home base the robots go to. They're synced up to GPS, they're synced up to internet, Starlink, whatever it's going to be, 4G, and they're basically querying whatever they need from the world, whether it's instructions from the people overseeing the project, or whether it's weather forecasts. Eventually we are going to work that sort of thing in to try to get as much of a cohesive end-to-end system as possible.
Well, first of all, very cool work you guys are
Thank
doing.
you.
It's really neat stuff. So have you guys either used or considered using synthetic data, some sort of like cornfield video game for driving around?
It'd be fun, yeah. Simulation can be useful for a couple of reasons. One of which is that it's actually a good way to generate labeled data. Like labeling is a huge bottleneck, and so if you can get an accurate enough simulation, the simulation can tell you this pixel is not only a corn plant, but it can tell you it's this specific corn plant and not this other corn plant. You can track it and that sort of thing. So we actually have started looking into this stuff. There's some pretty interesting results so far. Yeah, so we're looking forward to see what it can yield for us. Especially because corn, like, it only grows here 3 or 4 months of the year, and there's 12 months of the year and that sort of thing. So it's best to just be able to access these things year round. Yeah. Yep.
Have you experienced with your data labeling and analysis the problem of like, I think they call it distribution shift. So like the industry has a certain type of soybeans, but you throw in a wild ancestor in there and the model is just like, it can't figure it out and it's totally inaccurate estimate.
I haven't seen that too much. Usually it's hard enough getting it to work just for one setting. But in my experience, it tends to generalize pretty well. Yeah.
I think you have a question.
Yep.
Can I respond to that? I work with Michael. One thing I have seen, like just when I left the office, we went to India to gather a bunch of data on corn, and all that data we gathered, I trained a neural network on it, and then I ran that neural network on some corn on data we gathered in Illinois from previous seasons, and it did not generalize that well. So I do think there is that. It might just be the time of day, the color of the soil, all these things, but maybe between breeds we haven't seen that problem, but definitely the specific setting that you're gathering can have a huge influence on how effective your neural network is. So you got to make sure to gather different locations, times of day, all that kind of stuff.
Yeah, that'll definitely affect things. Sometimes you'll have a great view of the plants, but like the sun is setting in the background and it just washes out the whole image. So that can throw your system for a wrench. Yeah. So there's all sorts of weird, unexpected things that can happen.
Yeah.
Yeah.
This is kind of related to that. I knew someone years ago that was working with robotics that went into rescue in like bombs, right? Like when a place got bombed. And so like there was this whole vision problem of, oh, I know what a kitchen looks like, but now it's blown to smithereens. And in the same way I could imagine, like a farmer wants to know how many soybeans they have or how much corn they have. A storm comes through, tornado wipes it out. They want to recount. They want to know how many of their plants are viable. Like, how robust is it to the natural disasters that are going to affect that sort of count?
We haven't explored that exactly. The more changes there are relative to whatever data we train on, the more problems there are probably going to be. I think that in general, the best solution to that is always just make sure that we're gathering as diverse of data as we can, different field conditions, different crop qualities, different crop health, that sort of thing. Just make sure all of that's included in our training data sets.
Plenty of work to do.
What was that?
There is so much work to do, but it's really impressive where it is so far.
Thank you.
You said it's autonomous driving around the field, right?
Yeah.
So how are you going to factor in for the rats, squirrels?
Well, it hasn't become too much of a problem yet. I remember taking a trip to Texas last year. They warned me not to go to the field too early or too late because there are hogs that come out from the river sometimes, which might win a battle of inertia with our robots, you know. But so far, that hasn't been too much of a problem. We assume that we have a regular field without too many unusual things like that, and we're trusting that in future deployment, we'll be able to, the operator should be able to handle that, basically, that's what we're hoping.
I love visual
Yeah.
applications, like I've never heard about.
So this is a little bit more of like maybe a business or market question, so feel free to punt on it. But like, earlier on you showed that diagram of sort of like your input and your output, right? You're collecting all this data, and then on the tail end you're optimizing plants to be better, presumably. So if you were to put a human in between that, instead of all these machine learning algorithms, do you have a sense of like the ROI for this type of a product yet, so that you're going, look, if you go and count these, you can optimize your plant like this, and if you have a robot count them, you optimize for that. Like, what is the return for doing all this automation?
Yeah, I don't have the numbers for that off the top of my head. It'll vary drastically depending on the task. There are some things that it's just like completely impractical for a human to do, like soybean pod count. To have a person do like and count every soybean in a row it would take them hours to do like whatever I can do in 5 seconds. Whereas like measuring, say, stem width might take like 5 minutes for them to do a plot, whereas we take about 5 seconds. I would say that on average we can probably get about, all things considered, we can probably get about 100x improvement, specifically in the phenotyping space. Somewhere between 10 to 100 times. That would just be my guess. Yeah.
How often do you ever have to go out and rescue the robot when it gets stuck?
Well, we're mostly in the development footing for Terra Preta and Terramax, and so sometimes these things do have to happen. We're still figuring it out and that sort of thing. So for Terra Preta, we're still planning on the fact that we may not get perfect autonomy all the time. The way we budgeted it out is that it's okay if it crashes, like say, if we have 10 robots going out and they do down and backs planting through a field of corn. If there's a need to recover one, say every 3 or 4 passes, that's currently economical in our estimate because we can have a small number of people manage that many robots, and every once in a while one has to go and rescue the robot. But overall, the purpose is not necessarily perfect autonomy. The purpose is more having a system that is autonomous enough to be deployable and to be very profitable and useful to the customer at the end.
Interesting.
How do you choose the plants that you work with for your data collection process? Clearly, you need to have diversity in your data sets, but are there any specific factors that you consider, or is it purely on what you basis?
For clients, it depends on the project. For phenotyping, it mostly depends on which clients are coming up to us. They may have some unique things going on in their field, so they may want us to just focus on their situation. Like they might have unusually tall or short corn, or it might be in a greenhouse or something like that. In general, we try to develop our algorithms as specifically as possible and leverage what we've seen from different places. But when necessary, we've had to do customized solutions for customers, yeah.
What does the maintenance look like for your robots, and also like what is like the lifespan of one of these?
The lifespan I may not be able to answer. I think for maintenance, well, the plan for development is different from the plan for production. So we do more fixing on the ones that we're just prototyping, of course. Someone else would have to answer on what it will look like in production, yeah.
So is there a reason that you guys focus on ground robots only? When should I use drones to monitor your fleet of your robots?
Yeah, when we started with ground robots, because the phenotyping customers were mostly interested in what was going on under the canopy. Before I joined the company, I've heard that we started doing drones, and then customers said things like, "Can you get the drone to go under, like a foot above the ground?" And so we switched to ground robots because of that. And so one reason is that was the skill set that we developed from the start and the tech stack that we developed, and it became easier to, say, iterate upon ground-based robotics. But for the various projects, we think that it makes more sense to have ground-based robotics. For example, for Terra Sentia, obviously that one being on the ground, seeing the plants from the low view, it lets us see things that we couldn't from on high. For Terra Preta, where we're delivering large batches of seed, currently we're setting it up so that we can put 100 pounds of seed in the hopper. And so there are companies that are doing drone-based solutions to that, but they have their own separate complexities with battery management. Carrying that much seed on a drone means that you need to have a very large drone, that sort of thing, and pricing plays in. So I wouldn't be able to answer the specifics of the pricing there, but that's basically the reasoning that we've gone into. And then with a larger robot, there's no way that a drone could do what Terramax could do, for instance. So that one kind of takes care of itself. But yeah, that's the best answer I can give.
Thank you very much.